Section 2.1, the tangent and velocity problems. This actually gives us a great introduction into why we even study calculus. So first, the tangent line to a curve is a line that touches the curve and should have the same direction as the curve at the point of contact. Our goal is to make this definition more precise. One simple understanding of the tangent line is on the circle. The line that is tangent to the point on a circle only intersects the circle at one point. So for example, if we were just to draw a circle, a tangent line at a point would just touch the circle at one point and then continue on. If you were to draw a line that was inside of the circle, that would of course intersect at more than one point, so that wouldn't be a tangent line. So it's just touching the circle at one place. However, when we try to do this with a more complicated curve, this fails. So for example, if we were to look at a sine wave, like this, and then draw a tangent at a certain point, like maybe here, we can notice that it touches there, but then if we were to keep this line going, it would intersect with the graph again. So we need to be a little bit more specific when we're talking about a tangent line to a curve at a point. So we'll look at this example. Find the equation of the line that is tangent to the parabola y equal x squared at the point P at the coordinate 1, 1. All we really need for this equation of the line is the slope, because then we can use the point slope form of the line since we are given a point P 1, 1. To find this slope, we will first find the slope of what is called the secant line through P at 1, 1, and then another point on the curve, which we will label with a variable, Q at coordinates x, x squared. We'll use values of x that are closer and closer to the value of x equal 1 on both sides of that point P, and we'll see what the slope approaches. Note, a secant line is one that cuts a curve in 2 points, so like what we saw with the sine wave. So for example, let's start with a point x equal 1.5, and then find out what the slope is. I have it written down there, but let's just draw a little graph of our parabola just to get us started. So if we were to look at that parabola, y equal x squared, we know that it has its vertex at 0, 0. We already know the point 1, 1 is on the parabola because that was given to us. And of course, if x is equal to 1, then when we square it, we would get y is equal to 1, so that gives us another point. And when we square positive 1, we get positive 1, but when we square negative 1, meaning x equal negative 1, we also get positive 1. So that gives us another point. A parabola is a very famous function from pre-calculus you would have seen many times, and also in algebra, so hopefully at this point we are familiar with it. And if we want a couple other points, we could of course do x equal, say, 2, and then x equal negative 2. So as a little sketch for our parabola, when I square 2 or negative 2, I would get y equal 4. So there's some points for our parabola, and it just looks like this as a little sketch. There's our parabola y equal x squared. Just plugging in some points. So then what we are focused on is the point 1, 1. And then for this first bullet point, I also want to look at when x is 1.5. So that would be halfway between 1 and 2. That would intersect somewhere up on the curve. So when we want to figure out where does it intersect, we just take when x is equal to 1.5, y is equal to 1.5 squared. And then we could just use a calculator, 1.5 times 1.5, and that gives us 2.25. So then the slope of the line that connects these 2 points, that would just be y2 minus y1 divided by x2 minus x1. And you can see that's what I had already written here. 1.5 squared, or 2.25, minus 1, that's the difference of the 2 y coordinates, divided by the difference of the 2 x coordinates, 1.5 minus 1. That gives us 1.25 divided by 0.5, and when I divide those, I get 2.5. So that's the slope of the line that connects the point 1, 1 and the point 1.5, 2.25. So now this exercise is saying, let's now make the x coordinate even closer to x equal 1. So this next value will be when x is equal to 1.1. If we want to find that slope, that would again be y2 minus y1 divided by x2 minus x1. But this time, the x coordinates are 1.1 minus 1. And then to find the y values, remember you can just use the function, so 1.1 squared minus 1 squared. So then 1.1 squared is 1.21 minus 1 squared, which is 1, and then 1.1 minus 1 is 0.1, and then 0.21 divided by 0.1, that is 2.1. So what we want to focus on is as our x value is getting closer to 1, 1.5, and then 1.1, notice that our slope is also maybe approaching something. So we're going to do one more. When x is equal to 1.001. Again, the slope would be y2 minus y1 divided by x2 minus x1. Using what we did in the previous example, all I have to do is just square the respective x values and then subtract. And then on the denominator, it's just the subtraction of the x values. So then 1.001 squared, that's 1.002001. And then when I subtract 1.002001 minus 1, and then divide by 0.01, that just gives me 2.001. So what it seems like is as my x value keeps getting closer to 1, my slope is approaching 2. It seems like the slope appears to approach the value of 2 as x approaches the value of 1. In this manner, we say that the slope of the tangent line is the limit of the slopes of the secant line. Notationally, what I have written here on this line, we would write the limit as the point Q approaches the point P of the slope between the points P and Q is equal to m, the slope of the tangent line. And then also using our function, limit as x approaches 1 of the formula for slope, which is x squared minus 1 divided by x minus 1, because that's all we were doing this whole time, was just taking a value of x and squaring it and then subtracting 1, and then in the denominator subtracting x minus 1. That is approaching 2. So what I've just written here in green, this is what we are going to be getting to in Chapter 2, is actually learning about these things called limits, and then this notation that I'm using here with functions. So then to answer the question, if we assume that the slope is 2, then using the point slope form of the line, we get that the equation is y minus 1 equal 2 times x minus 1. Here the slope is 2, and the point that we were using was 1, 1. And then writing that in slope-intercept form, y equal 2x minus 1. So now that's the tangent problem. Let's see how this also applies to what is called velocity. When you are driving in a car or riding on a bike or walking or doing anything that involves movement, you know that your speed is not constant. You start, you stop, you speed up or accelerate, and you slow down by braking. On a bike, on a car, you would use brakes. If you're walking, it's just coming to a stop and then starting up again. So then what about your speed at a very specific moment? A snapshot. Can we specifically define the instantaneous velocity at any time? Let's look at this problem. If a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, meaning that's its initial velocity, its height in meters, t seconds later, is given by the equation y, which stands for height, equal 10t minus 1.86 t squared. So first, part A, find the average velocity over the given time intervals, 1 to 2, 1 to 1.1, and 1 to 1.01. Here you can notice that these intervals are intervals of time, which means in part I, 1 to 2 seconds, so an interval of 1 second. And then the next interval is shorter, and then the third interval is even shorter than that. So we're going to start with finding the average velocity first. For part A, to find the average velocity, think about average speed. This just means take the distance traveled between 1 and 2 seconds, and then divide by the change in time, just like finding the slope between two coordinates that we did previously. So for part A, for average velocity, we can think of this as the distance divided by time. To figure out the distance, it really just means the change in position. So, change in position. And then what we are going to divide by is how much time went by, so the change in time. To figure out the change in position, remember that we are given position as height, and that is given by a function. So the change in position is where is this rock in part I at 2 seconds, and then where is this rock at 1 second, and then find the difference between those two. So I'm going to write this as y evaluated at 2 minus y evaluated at 1, and then divide that by, just like we did in the previous example, the given independent values, t equal 2 and t equal 1, I'm going to subtract those. So then y of 2 just means plugging in 2 to our function, which just means 10 times 2 minus 1.86 times 2 squared. And then I also have to subtract from that what is the value of y at t equal 1. This would be 10 times 1, which is 10, minus 1.86 times 1 squared, which is just 1.86. And then we're going to divide that by 2 minus 1, which is just 1. Some of this stuff you're going to repeat as we go into the other parts for 2 and 3. It's really just going to be, we keep evaluating our function at 1, since that's the first coordinate in these time intervals. So for what I have written here, 10 times 2, that's 20. 1.86 times 2 squared, or 4. That gives me 7.44. and then I have to subtract the value 10 minus 1.86, which is just meaning subtract 8.14. And then I divide all of that by 1. So this just becomes 20 minus 7.44 minus 8.14, which is 4.42. Divide that by 1. And then we want to think this is talking about velocity, which they gave us an idea of the units for velocity before, meters per second. So it's the same thing for us, 4.42 meters per second. So this would just be for part I. So for the other two, I'm going to set this up just by using the pattern we saw before. Now for part 2, we're going to evaluate at 1.1 and then at 1. So your average velocity will be y evaluated at 1.1 minus y of 1, and then divide that by 1.1 minus 1. And then for part 3, it would be y evaluated at 1.01 minus y of 1, and then divide that by 1.0 minus 1. So take a couple minutes on your own, pause this video, and see if you can figure out what those are going to equal. And then you can check your answer after unpausing the video. So here's what you should have got for part 2, 6.094 meters per second. And then for part 3, 6.261 meters per second. So then part B, the question says, estimate the instantaneous velocity when t is equal to 1. This is as if there was a speedometer on the rock, and you could look at it right at 1 second and see what the speed is at that very instant. But of course there isn't a speedometer on that rock, so we have to use what we're doing here to try to get this estimate. So what does it seem that the speed is approaching as the time interval is getting shorter? It seems that the speed is approaching. We could use the answer that we just finished with, the instantaneous velocity at t equal 1 is approximately, we could say 6.26, if we just want to use 2 decimal places, meters per second. How could we make this even better of an approximation? We have to make that time interval shorter and shorter. Maybe instead of 1.01 seconds, 1.00001 second. So very quickly after t equal 1 second. Then look at what happens in that short time interval. But you could keep doing that forever to make that time interval as short as possible. So what this is giving us a clue about is that we need a better understanding about what are called limits. What are these limits that we are approaching as we are making a certain interval shorter and shorter? And we'll continue that in the next section.